use in creating our PFDs. And we're going to understand the equipment symbols, and also we're going to be reading a PFD. So going forward, now the purpose of the PFD, one, to define the plant design basis, the basis of the plant design, which involves the project scope and objective. For example, let's not think about the English grammar. In simple terms, define the plant design basis. It means the production rate. For example, you want to produce water, and you want to design a plant that will produce water. By producing water, I mean maybe water treatment plant. So you will need to define the rate, how many liters per hour. So these are the things that your PFD would do. It will have information of this. It's going to define the production rate, the throughput of the plant. Then the project scope and objective. You want to produce water, clean water. What will be the composition of metallic ions in it, the magnesium content, the calcium content, the pH of the water? All these things will be defined here, to be defined on your PFD. Okay, so, and then also the operating philosophy of the project, whether it's going to be a continuous or a batch process, it will be defined on the PFD. So now also the design parameters, the source, the composition, the feedstock. What will be the feedstock? If you want to, if it's petroleum products you want to produce, then you define the feedstock, which is going to be crude oil, or if it's going to be butane or propane or ethane or methane or natural gas mixtures, all will be defined here in the PFD. Okay, and then also the source where it's coming from, and also the final yield. The operating parameters, the temperatures, the pressure, all the design parameters will be defined there also. Okay. Now, also, another thing that will be mentioned in your PFD would be the utilities and offsite. Because, for example, you want to, let's use an ammonia plant, for example. A plant that is going to produce ammonia. The feedstock for ammonia would be natural gas. And you need hydrogen for your natural gas, and you need nitrogen from air for you to be able to produce ammonia, NH3, okay, through Haber-Bosch process. For those who studied chemical engineering, you should be very conversant with this. You already heard about it, even if you don't know about it in depth. So the side processes would be water for production of steam. You need your compressed air. From your compressed air, you get your nitrogen. You need your blanketing system, and of course, you need the electrical systems that will power your valves, that will power your equipment and all of that. All these are utilities and offsite. Okay, they're going to be included in the PFD. They're all the contents of the PFD. Okay, so now let's go into the standards. And before we go into the standards and codes and numberings, anybody has a question for here, for what we just talked about? I want to be sure I'm not talking to myself because you're all on mute. Any questions? Did you understand? Yes or no? I need you to put a reaction. Either you put a reaction or you speak up so that I know that you're following. Okay, I can see some reactions. All right. Okay. So now going ahead, standards and numberings. Standards, numberings, and symbols. So there are certain standards that are required for your documentation and preparation of your documents. You have the ASME, you have the API, the OSHA, IEC, the ATEX, the ASTM, ISA, IEC, ISO. So what are all those things? Has any of you heard about this before? If you have, please put a reaction. Okay, Shahima. So Shahima, I'm going to invite you to tell me which one you understand, which one you know before now. Don't be shy.
Hello, please, can I speak?
Yes, you can go ahead and share with your colleagues and us.
So I saw it through standards and symbols. I understand all their full meanings, and then API, we actually use it for the calculations. That's the American Petroleum Institute. And ASM is American Society of Mining Engineers. And then
Mhm.
OSHA is an occupation based in UK. Yes, it's based in UK, but it has some other branches all around the world. That's occupational safety and health administration. Then ASTM is American Society of Testing and Materials, and then ISO is it Institute for Standardization? Yes, that's what I know about it. And I know that the API it's responsible for the. I think I just have some basic knowledge about it.
Okay, okay, that's beautiful. That's beautiful. It's good that you have some knowledge about it. That's great. Thank you very much, Shahima. Okay. Uh, does any other person know something about it apart from knowing the full meaning of the acronyms? Anybody? Okay, fine. Let me break it down into a simpler way. I will start with the ASME. So for the ASME, think of it as imagine your body, the human body, okay? And okay, someone is raising the hands. Is the hands for question or is it for contribution? If it's for contribution or question, please unmute and speak.
Okay. Hello, sir.
Yes, yes, yes.
Okay. Good evening, sir. Sorry, I was having an issue with my other phone. So, for I'm aware of API, ASME,
Mm-hmm,
ASME. The API is the American Petroleum Institute
mm-hmm,
that governs and regulates procedures for tank. I know of tank farms, and it's actually a standard for tank farms, erections, and mechanical work. Then I know of OSHA. OSHA, because I did a process safety management course from OSHA, and I'm aware of OSHA. I'm also aware of ISO, Institute of Standard Organization, where
mm-hmm.
we had to do a course regarding that for getting it was for water treatment. It was a short course for water treatment. Then I know of ASTME. It's majorly for it's an organization that covers materials and equipment, the sizing of the materials, as well as the type of material sizing, probably a carbon steel, the steel mostly for steel plates, the type of steel plate that is being used for mechanical erection, and it's like that. Thank you.
Thank you very, very much. Thank you very, very much. That was a very, very good contribution. Very, very good one. Okay, let me break it down for those who have not heard about it before. So, uh, imagine your human body, your body, right? You have veins going through your body, it's pumping blood through your heart and through your nervous system and everything. So now these need to be contained at a certain pressure for it to be able to flow around your body. right? If it exceeds this pressure, your arteries are get busted. So the ASME the is like a rule book for building the arteries and veins of the plant, which are the pipes. The pipes, these are the arteries and veins of the plant. So it's like a rule book guiding this, and to help withstand pressure from eruption in the pipes and vessels as well. So this is what ASME does for you. It's like a rule book for standards for your piping and the safety of your vessels and piping. Then for API, now API has to do with your tanks and your flare relief systems. Uh, by relief systems, I mean, for example, you have uh, pressure buildup on a line, and then you have to release a bit of the gas in that line to relieve the pressure so that the pressure will go below the design pressure of the pipeline. Because every line has a design pressure. Okay, it has a design pressure, it has an operating window, and then it has a safeguarding window. Uh, Let me explain it this way for you. All right, imagine you have a pipe, and this pipe now, okay, let's use the gas cylinder you have in your house. The gas cylinder you have, for example, you have 12.5 kg, and is rated maximum defined maximum pressure is about let's use for example 5 bar maximum pressure, right? This is the maximum working pressure of this. It means you shouldn't exceed this pressure in your uh in this vessel. You shouldn't exceed this pressure in your cylinder. So now you have a limit where you can operate between. Let's say you are allowed to operate between 0 and 4. So you allow approximately one bar, and not so that you don't ever get to 5 bar. Okay. Now this 4 bar now becomes the pressure which you will use in designing your plant or your equipment. That whenever pressure gets to this point, you should relieve at 4 bars so that it never gets to 5 bar. So there's an allowance for it. So this API guides the laws and the rules for the design pressure of your relief valves, your flare systems, and storage tanks, and all whatnot. Okay, so that's for API. Then we have the OSHA. We have the OSHA. So these are standards for people who are actually working in the plants, the operators, the safety personnel, the managers, and everybody that has to be on the plant. This is a standard for people who are working in the plant. So it tells you how to handle some materials, how to handle some operations, and the safety, the PPE is required for it, and all of this. So that's what OSHA does for you. It's also is a very important standard. In fact, OSHA is one of the most important standards in every plant that you have, be it an oil and gas plant or just food factory. OSHA is very important. Okay, so yeah, so that's about OSHA. Then we have the ASTM, which is for materials and material testing. So usually, you'd have, for example, a a a glass bottle containing maybe a chemical or let's say acid. Now you have your material sheet, data sheet there. ASTM guides all of this. We have the MSDS, material safety and data sheet, at the back of this bottle containing the acid. It tells you how to handle it, how to take care of it, how to prevent spill or accident. So this is what it does for you. And also, it also has rules guiding um, your the right materials to select for your pipes, right materials to select for your coatings of your pipes. For example, like one of us had already said, whether you use carbon steel or you use stainless steel. Okay, so this ASTM this is what it does. And then you have ISA. Now, ISA has to do with your control and instrumentation. Imagine driving a car and then you don't have a dashboard. So you need a dashboard to give you feedback and tell you, okay, you are over speeding. You're now clocking over 200 kilometers per hour. Slow down. This is what ISA does. It's like your control system. It keeps you alert, right? It also has to do with the alarming systems in your plant, the safety instrumented systems. So all of these standards, they all work hand in hand to ensure that the plant is working at maximum yield and safe, right? And also you have the ISO. The ISO, it has to do with okay. ISO is like the good citizen certificate. It shows that, oh, this plant is certified. These plants will not cause harm to people. These plants will not cause harm to the environment. Okay. So this is what ISO does. So ISO is for quality, environment, and management. This is what ISO does. So with these standards, it shows that you care about the world and also the safety and sustainability of the environment. This is what these standards do. And remember, in the previous meeting that we had, we talked about the engineer who is responsible for these codes. Somewhere here, I have to go back. It was yeah, the standards and code specialist. So for every industry, for every plant, they have to ensure that they are aware of this, and the specialist gives provides the documents for these codes and the standards. The process engineer also is always aware of this as well, and then he uses it to design the plant. So without these standards, there's going to be problem, because anybody can decide that, okay, I want to draw this, and then you decide whatever symbol you choose here. Let's say you already know what a heat exchanger looks like in real life. You decide to draw a heat exchanger the way it looks like here. And then there is another plant close by, your neighbor. He wants to design a heat exchanger. He wants to draw a heat exchanger. He draws something else. So these standards guide all engineers across regions, countries, everywhere, to ensure that they maintain homogeneity of the drawings, the standards, the laws, the rules, and regulations guiding all of this operation and the development of this document. So it's important to know these standards. Without it, there will be chaos. Without it, there's going to be chaos. Without these standards, you're going to have chaos. Because imagine, oh, yeah, you can decide, oh, I'm going to rate I'm going to rate the relief pressure of my valve on a line carrying gas at so and so pressure. I'm going to put it at whatever I want, you know. So these standards are what help you to stay within a particular uh, regulatory limit. That's why they are important to know. Okay. All right. So now going forward, do you have any questions here? Any questions for me? If you have questions, please raise your hands. Anybody? If you don't have questions, we'll go forward. And I hope you're understanding what we are saying. I hope you understand what we are talking about.
Yes, sir.
Okay. All right. So, please don't take this for granted, because just because you're not actually doing, you might be. This is one thing about people when they want to go into process engineering. They have very high expectations to go into. Okay, let's go into doing something, creating something. But then if you miss the foundations, you miss it. If you miss the foundations, you miss it. You're just going to be someone who just draws. You just draw something, right? So you need to understand all of this before you go deep into the meat. Okay? So because if you don't understand it, you're gonna cause chaos. You cause serious problem. And imagine you have a project for $2 billion. These days, it costs so much to build a refinery, $2 billion, and it's your responsibility to come up with a PFD, and then you come up with a document that's going to cause confusion. Everybody knows a heat exchanger to be of this symbol, and then you choose something else. So these standards are very important for you to know. Okay. So since you don't have questions, let's go ahead and go into the next thing. So I'm going to focus a bit on the ISO standards, and because they are what shows that the rest of these are okay. The moment you start, a company acquires ISO standards, any of these standards, any of these pillars of standards. Usually, if you visit companies, usually at the reception, you find some frame, mostly at the reception or somewhere in the entrance, just usually at the entrance. You find a frame showing, oh, company has ISO this, ISO 9001, ISO 14001, and all of these standards. So what it means is that they have they are certified for quality, and that means that they have customer trust and efficiency. It means that their customer trust them. So they have good customer uh, relationship because they provide quality. So they're not going to disappoint their customers in whatever product they're going to provide. Okay. And now you have ISO 14001. This is about the environment. The company is responsible for sustainability of the environment, and they have to comply with every single uh, rules and regulation guiding them to maintain the environment which they've found. Okay, the water, the emissions, the land use, and all of this, they are all under the ISO 14000. Please, I have a hand up. Marshall, speak.
Eh, Yeah, thank you very much. So
Okay.
I have a question. These codes, do they have any, what's their relevance to PFD? And are they meant to be shown on the PFD? And when you see it on the PFD, what does it tell you? Thank
Okay.
you.
Yeah, you're just meant to understand this because the reason you need to understand this is because before you start your PFD, there are lots of stakeholders who will be involved in the design basis, the concept, and then they have to ensure that whatever thing they are planning has to be guided by these rules and regulations. It's just like let's assume you have money and you buy an island and you decide to start a country. You start a country and then nobody is under any rule or under any law. Everybody does what he wants. For example, let me go to local to what we can see, what we can relate with. You want to start you as usual a water treatment plant, and then you decide that okay, what you use in treating your water is salt because nobody is looking after you, nobody is putting you on check. So you use salt, you put salt in your water, and then you've treated your water. I don't even understand. So now these standards are what forces you to ensure quality. For this one, quality. For this, environment. For this, health and safety. For this, energy. For this, information security, food safety, and social responsibility. But these are the three main pillars. These three. These three are the main pillars. So as a process engineer, it's important you know them. These three are the three main pillars. The rest could be for some other industry or some other facility. But these three are the main pillars. I don't know. Did you understand, Marshall?
Yes, I do. Thank you.
Okay. So for the rest of the standards, the rest of the standards are what will guide you in choosing the right equipment because it's not just about the drawing. The PFD is going to contain information about what type of material your vessel will have. It's going to contain the type of material, whether it will be a carbon steel or stainless steel. We're going to see a PFD, and okay, we're going to see the legend of the PFD in this lesson, not the PFD after all. In the next lesson, we'll see a PFD, and then we get to see all this information. You see the pressure, the temperature rating, the maximum pressure, the maximum design pressure, the maximum design temperature, yeah, the type of material, whether it's carbon steel or stainless steel, and all of this. And then we're going to see the temperatures for your relief valves and all of this, and then the materials for your tanks and whatever, all those things. So mostly these ones you have this information on your P&ID, but these other ones will be used in the designs. They will be used in the design. These ones will be used for consideration of what you want to do, the location you're going to place some of the equipment or some of the units of the plant, some of the units operation. If there are areas that require that have hazardous substances, then the choice of location will not, needs to be put into consideration, of which these will be discussed in a meeting. So and of course the ASTM, the materials and equipment and the rest of them. So now going forward, yeah, I already said why are these standards important? First, consistency in drawing. The drawings needs to be consistent, such that any engineer who goes from one site to another site, or you transfer your job, let's say you move from Shell to ExxonMobil, excuse me, you still see whenever you see a valve, you know it's a valve. You see a vessel, you know that's a vessel. You see a storage tank, you know that's a storage tank. The same. So of course there are there are varieties of drawing for one particular equipment. So but for each facility they choose which one they are going to follow, and they maintain it and remain consistent with that. So now of course, like I said, to prevent chaos, otherwise every engineer would draw differently. So I wait. So otherwise every engineer is going to draw differently. You draw whatever you wish to draw. Okay. All right, so now let's go into understanding the equipment symbols and reading the PFD. This, I have to zoom it out a bit and start from the top left. So I hope you can see this properly. So we're going to go from this part, all right? So these, if you can see this, this is kinds of lines, the kind of lines you find on the PFD. Can you see this? Please, I need you to respond or a reaction so I can know that you are following. Okay. All right. Thank you. So the kind of lines you find the main process lines, which is thicker, the main process line. Then you find the secondary process lines or the utility lines, which I already mentioned before. I mentioned the utilities, which can have instrument air, for example. If you have a plant that is refining crude oil, you don't need air in the process, but you need air to control your valves. You need air to control the pneumatic valves, and you need your electrical signals for you to send uh, either analog or digital signal to the valve to open and close the valve, or to vary the valve according to whatever the process is. So all these lines will tell you, okay, this is what this is doing at this point in time in the drawing, and this is exactly what you're going to find in the field. So when you go to the field, you're able to identify, okay, lines that are broken like this are the electrical signal lines. The lines are not thick. These ones are the utility lines. Usually the 2-inch or the 1-inch lines you see in the plants, in the physical plant. So, so with this lesson, you'll be able to quickly understand any plant drawing you see. The moment you start a new job, you reduce your retraining time, or the time you use in catching up with what's going on in the facility. In other words, with this training, you can boldly apply for a job and try and talk about all of this because you now have the knowledge of this. Okay. All right. So Going forward, you see a thick line is a process line, the main process line. For example, you have natural gas you're processing. It's natural gas that will be on the thick line. That's the main line. Then the secondary process or the utility lines. It could be, for example, like I said, nitrogen or instrument F, and then the electrical signal on instruments. All right. Going forward, then we have line crossovers. Line crossovers. So for these two fake lines, you have two main process lines crossing over. They don't meet. They don't meet. They don't mix. They're not mixing. They're just crossing over because of the scale of the drawing. You're putting it in one scale. So uh, and you want to put them in the same drawing. Okay. All right. Then another crossover here, main line and secondary line, of course, and then main line and then instrument line. These are crossovers. You need to understand all of this as well. Just give me a moment. Okay, so now notation of lines and battery limits, tie-in points, and all of this. So battery limits, and does anybody know what a battery limit is? Anyone? You probably must have heard this from your workplace or your IT experience if you've served in some plant. So if you know it, can you just raise your hands? Anyone? Okay. Okay, your microphone is malfunctioning. Okay. Houses the crude distillation unit and the main process equipment. Okay. Okay. Okay, battery limits, thank you for that. Battery limits is basically where the main process starts. Uh, Let me see from the previous diagram if we can find the battery limit so I can explain it to you. Where is it? Okay. Okay. For example, this is battery limit. From this point is a battery limit in this drawing. But you don't see the other sections of this plant. This is just the beginning of the plant. Before here, there are other equipments. There are other equipments that come here. There are drums, knockout drums that are going to knock out heavy fluids and moisture before it comes into this coalescing filter. Like I said before, is a filter. So there are other equipments that will be here, but they are not the main equipment. So the moment the main equipment starts, that's the battery limit. So that's the battery limit. So back to where we were. So you find things like this from item number this to so and so place. You see the other one at the other edge. It's going from one process to the other. Okay. So but on the other diagram, it was a different shape that was used. It was more like an arrow. If you saw it, it was more like an arrow. So for different companies, they can decide to choose one particular convention and maintain it throughout their documents. Then for utility lines, this is for utility lines. Cooling water is for cooling water. Okay, please take note of this because they're going to be your arsenals in PFD. Then direction of flow, of course, is simple. This is the direction where the fluid or the process or utility process is flowing, the direction of it. So it can be this way or whichever way. And again, for every document, PFD, BFD, P&ID, it starts from the left and move to the right of the process. So just like this one, all processes, it starts from this way, goes to the right, from the left to the right. Okay. Okay. This is what I was talking about before, but it's not very clear. Here you have the operating pressure, operating conditions. It's not very clear because yeah, the document was not properly scanned. So yeah, this is where you have this information: maximum operating pressure, maximum operating temperature, the material of the vessel, and all of that. And the name, the notation of the vessel will always be at the top. If you look at here, you will find this is a coalescent filter. The annotation is VH0101. It will always be above the the equipment itself. That's where you find the annotation of the equipment. So yeah, let's go ahead. So like I said, it goes from the left to the right. Okay. So going forward. Okay, back to where we were. So now let's talk about the instruments, right? The instruments, they have symbols that represent all the instruments you can find in the plant. You have the flow controllers, the flow transmitters, you have the level transmitters, you have the temperature transmitters, pressure transmitters, you have differential pressure transmitters, and all of this. So they have symbols that represent them. Okay. So these symbols are actually here. These ones are for the control system. These ones are for the control systems. It's called instruments here, but they are actually like they are digital devices. They're mostly digital devices that are able to perform calculations because they need to pick information from instruments in the field and then compare it with a certain set points to make a decision on what to do in the process if there is a change in steady state. Okay. All right. So these are symbols for your transmitters. FC for flow transmitter, LC for your level transmitter. In this case, this is, can we have this particular page after the class? Okay, sure, not a problem. Not a problem. So I'll share it. Uh, so um, so you have flow. In this case, this is FG. Sorry, this is FC. This is LG. This is LG. LG is a level gauge. There's a difference between a level gauge and don't worry, I'm going to show you images of these things we just talked about today. Today we're just seeing symbols, but we're going to see images so that we can have like uh, a pictorial imagination of what it looks like for those of us that haven't seen it. Some of us, most of us must have seen it, but for those of us that have not seen it before, we'll have the opportunity to see it live, and it's going to feel like you've worked in the plant, especially when you go for interviews, the way you're going to speak. Okay, you speak like someone who has some experience. So this is a level gauge. Level gauge is different from your level transmitter. Okay. Now, usually the title is usually FT, flow transmitter, right? But in this case, flow controller. There are two different things. The transmitter is in the field. The controller is the controller of the flow transmitter. We're going to see this in a P&ID because you not usually find the controller on the PFD. You find controller on the P&ID. Okay, so we're going to still do that. But for now, just know this for now. So flow for your flow, then level for your level controlling level. Now going to the valves. So this is a general convention for control valves, right? Sometimes you find something written here. It's either it will be written A around this little shape you see here. You find A there or you find M there. Those A and M they have a meaning. But the moment you see this, just know it's a control valve. All right. Now, if I cover this, and you just have a shape like this moving through this direction. Now, I think I need to draw here. so that you understand this properly. I think I need to draw. So if you have a shape like this, don't mind my drawing. This is just a normal valve. It's not a control valve. This is a manual valve. It's not a control valve. But the moment you have this above it, is a control valve. If you look up here, I'm going to zoom in a bit. If you look up here, this line, they are broken lines. This line is an indication that, okay, this is a control valve. And for you to have a control valve, it means it receives signal from somewhere. It needs to receive electrical signal. Okay. Let's imagine, let me look for something that you can control with the cable. Okay, the Christmas lights you have in your house, right? If you have Christmas light, for those who celebrate Christmas, you plug the light. The light is like a string with bulbs everywhere. You need to plug it, right? And then there's a controller. You use that controller to either put the lights on or put the light off, or to dim the light, increase the brightness or reduce the brightness, right? I don't know if you remember all of this. Most of us as kids, we had all of this in our houses. Some used to sing some songs, make some sounds with songs and all of that. So there is a wire. The wire is connected to the light. And then you have a controller somewhere. The controller is what controls this light. So this this dotted lines is a representative of the cables that will lead to a control room where it could be clicked open or closed, right? So this is a representation of it. Remember, this is your process line. We have already started, guys. We've started already. So this is your process line. Remember the thickened line, the main process. That's what this is. Then the arrow direction. So the arrow direction that I already showed you, and then the main process line, which is the thick one. Okay? Excuse me. And then don't forget where is it? I just missed it. The electrical line that I just explained to you. Okay, yes. The electrical line. That's it here. So we just saw it here in this diagram. That was too fast. Okay, so this is the electrical line controlling, and this is your normal valve without any control. So I'm going to clean this very quickly. Okay, now you have another valve. Now I have this question for you. Please, I need you to unmute your mic and prepare to answer this question. This valve, is it a manual valve or is it an automatically controlled valve? You can okay, don't unmute your mic. You can just put the answer in the chat box. Let me see what your responses will be. Just use the chat box. Is it a manually controlled valve or is it an automatic valve? Okay, we have one response. Okay. I need everyone to respond. Everyone needs to respond. I need everyone's response. Okay, we are 14 in this meeting, so I want to see everybody's response. Oguche says manual. Okay, so only one person manual so far, or just automatic. Okay, Jones was logged out. Don't worry, I will explain it again. I need to see the responses of those who were here before to be sure we are all following. Automatic. Please don't be shy. Just put in your responses and put it very fast. Please don't use Google or anything because it won't help you to use Google and all of this. We're learning here. We don't need to be perfect. We're all learning. So just put in your responses quickly. It doesn't take time. Just type it. You can type A or M for A for automatic, M for manual very quickly. Let's not waste time on this. Okay, I'm going to make use of the responses I already have because our response is kind of slow. So Okay. The truth is that it's an automatic valve. It's an automatic valve. It's only a manual valve when you see this. Only when you see this. And it becomes automatic. Jones, I hope you're paying attention. It becomes automatic the moment you see this. It's an automatic valve. Okay? So manual without this. So this is a manual valve. And this is automatic, and this is also automatic. The difference is that this is just one directional valve, but this is a three-way valve. In this three-way valve, it can go either this direction or this direction, or, well, this direction. Whichever direction it can go. This is actually two-way valve, not a three-way valve. Please don't mind this. This is two-way valve. It can go this direction or this direction. Except it can actually go in reverse direction. Then it's a three-way valve. Okay? But it's controlled automatically. You can also have a manual three-way valve. Okay? But this one is an automatic three-way valve. So the moment you see this, it's controlled. It's automatically controlled. So let's go to the next part. We have finished the first line. Let's go to the second one. And yeah. So the second one, this is usually at the. Are you familiar with this? Have you seen this somewhere before? Does it look this table?
No, sir.
Okay. Yeah. The reason why you've not seen this is because we only have on this PFD we have here. So this is for your information. On this PFD is the front page. This is the front page of the document. So behind are the last few pages or the appendix of this document, because this document is not just one sheet. There are probably maybe 60, 100, 200 sheets, depending on the volume of the project. Okay, so it's going to be the appendix of the sheet. So, and the appendix of the sheet, you find the material balance, material energy balance information. On the PFD, only the PFD has this information. The P&ID does not have the heat and material balance sheet. We have noise coming from somebody here. Please, can you mute your? Okay. All right. Post, thank you for muting. All right, back to what we were saying. Oh, I think. Oh my, even my video. All right. So guys, back to what we were saying. We have this will be at the back of the document, right? Behind the document. That's where you find this document. So you won't find it at the front pages or the early pages of the PFD, or behind. So now another information you find. Okay, we already did this, the piping and pipeline symbols. So the main process line, the thick line, the secondary process, the faint line, then existing line, future line. All right, do not confuse yourself with all of these ones. Just pay attention to main line and secondary line for now, and also the electrical line. Okay, because this document is not very clear, so you might not be able to spot the difference between the electrical line and these other lines. Okay, because the electrical line is a dashed line. But if you can see properly, you see that the existing line here, it has a dash, a dot, dash, dot, dash, dot. If you can see it properly, but if you can't, no problem. Don't worry about that. Okay, so then we have the piping trap function symbols. You don't need to worry yourself about these ones much. for now because they are for steam trap and all condensate release. So later you get to know more about this. For now, you don't need to worry yourself about it. For now, okay. So now these ones are kind of more important. You need to focus on this one, the vents. The vents, for example, remember when I talked about your relief system where there's a pressure build up in the pipelines, and then if you don't relieve the pressure, you might have explosion. So you need to have a vent, you need to have your relief line there, and the relief line will automatically relieve the high pressure to go back to below the operating window. Okay. Now I'm going to explain to you what I mean by this operating window. I think I need to explain to you before we go ahead. So I'm going to draw a line here. You have a line here. Let me reduce this thickness. So you have a line here, and then you have the up. Oh, not good. Okay, perfect. So this is a scale, for example, right? This is 0, and this is 5. This is the design maximum. This is design pressure for a line, a pipeline, for example, or a vessel. Okay, and then you have an operating window. You have an operating window. Let's say the operating window is probably at 3 bar. So it means you're operating this process between 0 bar to 3 bar. Now they have what you call your safeguarding system, your safeguarding window. This is to protect the system from explosion, accident, and whatever. So this is probably going to be around 4 bar. Okay. Now, but these are based on the standards, on the API standards. These are what these standards will guide you on how to design these equipment, the vessels and the pipelines. So on the line, you have your relief system. On your relief system, you have events where uh okay, there are two things. There is drain and there is vent. These are two different things. So you have a drain. A drain is also a vent, but the vent is at the top of a vessel, for example. But the drain is at the bottom of the vessel. And I'm going to show you in the next diagrams we're going to be seeing. So this is a vent. So you need to know that for now. And for these ones, these are also drains as well. These are also drains. This is like a drain, but with a flexible hose. With a flexible hose. Okay. And then other types of drain that you don't need to worry yourself about. Of course, we talked about level gauge before. Talk about level gauge. I'm going to show you an image of that in the next lesson. Then spray device. This is like a shower. Spray device like a shower. Then don't worry about silencer. Strainer filter. This actually changes. This could change. This actually changes. This convention is not very common, but in some companies they use this. Okay. So the next one. Let's go to the next one. Okay. One of the very important areas. You have shell and tube type heat exchanger. We have different types of heat exchanger, shell and tube, coolant, heating medium, uh, yeah, all of this. So one is the process side and the other is the working fluid side. So you have the process fluid and the working fluid. The process fluid is the fluid, the main process where you want to get your yield, while the working fluid is the one you're using to do work either for cooling or for heating. Excuse me. Either for cooling or for heating. Okay. So this is the symbol for your heat exchanger. Then you have double pipe heat exchanger, also a heat exchanger symbol. Then you have for your reboiler systems. These are for reboiler systems. It's also a kind of I wouldn't call it a heat exchanger. It's just like your pot for cooking. Yeah, it's used for cooking. Reboilers are for cooking. For example, you have your distillation column, and then at the bottom of the distillation column, you have a reboiler that's going to supply heat to the distillation column. Okay. Uh, do we have any questions so far? Any questions so far before we continue? If you have questions, please raise your hands. Am I going too fast? Am I going too slow? Are you hearing me? I need your feedback before we move ahead. Hello. Please, I need your responses.
Very well, sir. We have been following you so far, sir.
Okay. All right. Great. All right. So we now have another equipment. It's called your air fin cooler. So this is a type of heat exchanger as well, but it's is an air cooler. Okay. So it takes air from the bottom and takes it out. So you have forced draft and induced draft. There are different types. Okay. Forced draft and induced draft for cooling. They are also a type of heat exchanger. Okay. So you have the process. This is the main process line. Remember the thick line, main process line going through the air cooler, and then the air is blowing, the air is cooling the process. For example, the process is going in at 70 degrees, and then air atmospheric temperature is going in at maybe 25 or even 30 on a hot afternoon. So you're using 30 degrees to cool this. Just like the way you have water of 30 degrees trying to cool something of maybe 100 degrees. Okay, so you use air and then you pull it down. So the same here. In this case, you have a temperature control because, of course, for the air cooler, what you want to cool down is what you want to reduce is temperature, right? So you have a temperature control here that's going to control the temperature of the air cooler, right? Let's say, for example, the process you want here, you want the temperature of the process to be 70 and it's coming in at 120, right? So this temperature controller is going to tell the fan, the air cooler, to blow faster. Maybe at 20%, it's going to be able to achieve, let's say, 100 degree. So that's a 20-degree drop from 120 here. Let me write it here so that you have, let me see, 120 degrees at this point. And what you want here is let's say 50 degrees, right? You want 50 degrees here. Don't mind my writing. So you want 50 degrees here. This controller is going to tell the fan, okay, we want 50 degrees. So it's going to measure the temperature that he has here, right? And then compare it with this temperature and then decide at what speed it's going to run to be able to achieve this. So let's say it's going to achieve this 50 degrees if it runs at 100%. This is based on the design. So it runs at 100%, it achieves 50 degrees. If it runs at 90%, probably it's going to achieve maybe 60 degrees. Okay? If it runs at 70%, probably it's going to achieve, it's not going to achieve 50 degrees, probably around 70 degrees. Okay, now this is an assumption we are giving for you to understand how this thing works. Okay, so that's that. Okay, so now that's that, and then okay, there is another information here. It's called louver control. Louver control. Apart from the fan, right, and then the process that's going through here. Usually is a tube. There are tubes. Tubes are passing through here, and then the fan blows air through here and cools the tubes that are within this section of the fan, of the cooler fan. You can call it cooler fan or air fin cooler. All right. So there are louvers, like the louvers in the houses where you open and close. The old louvers before you started having aluminium. So it closes and opens. You try to help in optimizing temperature control. So that's what the louver does around here. So there's also a louver control. Okay. So, and we're gonna skip the box cooler symbol. Then you have the furnace symbol. The furnace are usually your heaters for heating the main. Okay, let me try to explain this in the most simple way. You have reboilers, reboilers we talked about, right? The reboilers need to receive heat from some other source, okay? And please, are all these operating on cross flow, or can they be adjusted to flow concurrently? Shahima, your question is for which equipment, please?
That's for the heat exchangers.
Okay, for the heat exchanger. These ones, right? They are counter currents. They're counter current flow. This is flowing this way. A counter current flow. Are you there, Shahima?
Yes. So you
Okay.
mean all the exchanges are operating counter currently? The furnace, air cooler, short tube, double pipe.
Mhm.
Okay, thank you.
So they are counter current flow. Right, so let's go. I was talking about the heat from the furnace that is going to supply your boilers. Now the heat from the furnace is like, okay, the furnace is a furnace. Yeah, the furnace is a furnace. It's just gonna heat at very high temperatures. I think probably the highest temperatures you find because they are supplying heat to reboilers. Where are the reboilers? Let's go to the reboilers. Yeah, they're supplying heat to the reboilers. So these are your reboilers. The reboilers receive either oil or mostly oil because uh, the oil will be able to absorb more heat compared to the water, and it retains more heat compared to the water. So you use oil. So the oil now is gonna be heated up here. Usually in the furnace you use waste gases in the plant, and then these waste gases will heat up this. Sometimes it could be pure gas supply, right? And then they'll heat up this furnace. In the furnace, you have refractories inside that's going to keep heat from escaping to the external environment. So now this oil will be sent to the reboilers, and the reboilers will use it to heat up the columns. The distillation columns, which you are using to for your fractionation or whichever process that you are doing with your distillation column. And then you have the pumps. Now the pumps, you have centrifugal, the rotary pump, the reciprocating pump. So yeah, this is a symbol for your pump. This is almost the most common symbol for pump. Whenever you see this centrifugal, okay, you have it moving like this, goes like this way, goes this way, out. Then you have the rotary pump, you have the reciprocating pump, okay? So now let's go to the next one. So the next one here we have here is your compressor. Okay, this is 10:42. We need to hurry this up because we have already gone past my budget time. And so, all right, for compressors, right? This is your centrifugal compressor. And for compressor, remember you are compressing. You're compressing something, right? And when you compress, what happens? Can you try to remember Charles' law, Boyle's law? What happens when you do compression? Can somebody say it before we go ahead?
Basically the pressure increases.
Mm-hmm.
Is that correct?
Okay. Pressure increases, and what about the temperature?
Yeah, the temperature also will increase when you compress.
Okay. And what about the volume?
Volume. I think that one
Why
remains
not decrease?
constant.
Huh? Should be
Sorry.
constant.
Yeah, I think it should be
Okay.
constant.
If you remember Charles' law,
Yeah, I'm just guessing.
Boyle's law, gas law. Okay.
No, really.
Well, all right,
I
fine.
think
Your volume is gonna reduce. So just think about a compressor this way, right? Symbol of a compressor. You send in a gas. You send in a gas. Compressor deals with gas. Remember, you send in a gas. Let's say, see this shape. This area is bigger than this area. This is where it comes in and it leaves here. This is the main process line, right? So it comes in here, right? At this point, it has higher volume here. But at this point, the volume is lower. Why? Because you've compressed it. So you compress it, the pressure increases, temperature increases, and then the volume what decreases. So that's a compressor for you. So, and then you have expander. You have expanders. Expanders work in reverse of the compressor, right? So it has a lower volume here, right? And then it has a higher volume here. And then it reduces the pressure, right? This is a typical Joe Thomson effect, a typical Joe Thomson effect. So in this case, you have um, you have a temperature will be higher. Temperature will be higher at this point, right? If it goes in at 50 degrees, it's coming out at approximately maybe 100 degrees because you've increased the pressure. The molecules are excited and then they are hitting each other and also the walls of the internal compartment of the compressor, right? So now in this case, you're now losing the space between the particles. When you're losing the space between the particles, they have higher volume, and then what happens? The temperature does what? It reduces. Cooling takes effect. Here, temperature will be high. So in this case, let's say for example, you have an equipment, downstream of this equipment, you're going to have a cooler here because the temperature will be very high. So depending on what you want to achieve, you have a cooler at the downstream of the compressor to cool down the temperature. Because the idea of the compressor is that you only want to increase the pressure, right? But you don't want high temperature. So for you to handle high temperature, what you need to do is to have a cooler downstream of this. So use a cooler, reduce the temperature, but the pressure doesn't reduce that much. Okay, so that's for compressor, and then for expander. Then for blower, blower is similar to pump, similar to a pump. The diagram is very similar to pump. Then we have okay, this is a compressor and turbine. And which one will be a turbine here? Which one will be a compressor? Because one is a prime mover. Okay, symbol of compressor and expander is similar to that of reducer. Yeah. It's similar to that of reducer. The reducer, you see reducer on the process. Okay, let me draw it. So what just happened there? Okay. Can you guys still see my screen?
Very well, sir.
Okay. All right. So my screen went blank for a while. So this is the process line, for example. Okay. This is the direction of flow, and you have this. Then it continues. See how it looks. It is small. The scale is smaller compared to the scale of the compressor you're seeing here. For a compressor, the scale of the compressor is going to be bigger. It is not, the compressor is not like something on the pipeline, but the reducer and expander is something on the pipeline, right? if you want to have a visual representation of it, it's going to be something like this. And then you have the reducer somewhere on the line. You have the reducer somewhere on the line here. And then the diameter changes from, this is what you see on the physical site. Don't mind my drawing. This is what you see on the physical site. The reducer will be somewhere here, right? And then this will be the direction of flow, okay? And then let's say this is, maybe this is 8 inch, 8 inch, 8 inch line. And then this will be 6 inch. That's what the reducer will do for you, okay? But for the centrifugal compressor, it's not going to be like this. It's not going to be like this. The centrifugal compressor is very large equipment, it's a large equipment, so it's not going to be on a process line like this. It's rather going to be entering the compressor. Let me use this as a representation of the compressor. So it's big like this. It's going to enter the compressor and going to leave somewhere. You know, yeah. So they're not the same thing. They look the same, but they're not the same. So I'm going to clean this now. Okay. Now my screen is blank again. I don't know if you can still see my screen. Something is happening here. Okay. All right. So, so which one is going to be a turbine here? Which one is going to be a turbine here? We need to wrap up very quickly. Please, I need your responses very fast. Which one will be a turbine? Please unmute your mic and respond very quickly. Between these.
I think sorry. I think the turbine is the one that has a steam entering into the second one. And the
Okay,
first one is the compressor.
thank you very much. That's the turbine. The turbine is the one with the steam turbine, and then it is the prime mover. It's gonna move the shaft. The shaft is gonna be connected to the compressor, and when it rotates, it's gonna rotate the the compressor as well. So this one has the energy. This one has no energy. This is just like, some box that has the ability to rotate, but it needs power from some other. So this guy is gonna give it the power. This guy receives power from steam, receives the energy from steam, and then the steam turns the shaft to rotational energy, and then rotates the shaft, rotates the shaft of this. So there's gonna be a coupling between between the turbine and the compressor, and then this will allow the compressor to work. So of course there's a flow control here because you need to control the flow output of the compressor, and that will determine how much steam the turbine will take. So more steam, more energy, more opening, and all of that. Less steam, less energy, less opening. So it goes from 0 to 100%, and then that decides how much opening you're gonna have and how much output you're gonna have. Okay, so these are column symbols. This is the most common symbol you'll find in the industry. This is the most common symbol. Everybody knows it. Usually a vertical column with numbers. If it's the tray type with the numbers, how many trays you have, starting from tray 1, and the last tray 25, 24 here. Sometimes it could be 20 trays, depends on the design. And of course, this one, the packed columns, where you have packings inside. Okay, so these two are the most common ones that you need to pay attention to for now. These two, which is very common. And then you have the drum symbols, you have the horizontal and the vertical drums for separation, your two-phase and three-phase separators for separating three phases, either gas and two liquids, like oil and water. That's for your three-phase separator. Usually, it's usually a horizontal separator, okay? And uh, there's no time to give you all these details, but just know, okay, horizontal separators are usually three-phase separators, okay? So it can be two-phase separator, but you can also design it to be a three-phase separator. Maybe in the next class, I'm going to explain to you And then you have the vertical separator, which is two-phase liquid and vapor. Okay. Then you have the reactor symbol, and now you have the tanks, the storage tanks for storing the products or for storing the feedstock, whichever the case. If it's for uh, organizations that do not have the feedstock, the source of the feedstock, maybe they have to buy it and store it and then process it from there. This will be their case. Give me a moment. I need to check this very quickly. Okay. So yeah, so that's for the tank symbols. So this is where we will stop for today. This is 10:54, and we have exceeded our time for today. So this is where we're going to stop. Yes, go ahead, Blessing Ben, and ask your question.
All right, sir. Thank you very much, sir. So I just wanted to ask in regards these all these symbols, especially for the P&ID. Do we have all of them, especially for a software like Aspen ISIS? Do you have all these symbols on the system, or there's a different software platform where we go draw these things ourselves?
Okay. First of all, Aspen ISIS is not for drawing these. Aspen ISIS is for simulation. That's a process simulation engineer, and that's what Aspen ISIS does. For designing and drawing of this, you use your AutoCAD P&ID or AutoCAD Plan Design. These softwares are usually online and paid. It requires that you pay for it. But there are also alternatives you can use for learning, right? Or you can decide to buy the license if you have the money. I'm not going to tell you to crack it because when you crack, you leave your system open to viruses and attack. So this is very important to also pay attention to this. I'm an advocate of cybersecurity, so I will not advise you to use unlicensed versions. So even in my computer, I don't have any unlicensed version. Everything is licensed or free version or for educational version. Okay, so for these drawings, you need the AutoCAD P&ID. So if you have access to it, I believe you can purchase it somewhere in Nigeria on the streets, on the CD, and then you install and you pay for it and install it. So, or you can even pay for it online, or the free version I'm going to introduce to you in the future lesson. Yes, it's not AutoCAD P&ID, but I will introduce to you. It's open source, so everybody can use it for free. And you have these templates. They are templates. So these templates are already there. You just pick it and drop it, connect the lines and all of that. So, so that's it. And you can use the same software for PFD and also for P&ID. Of course, the difference is just that one is more detailed than the other. So that will be it. I have a quiz for us, but the time is fast spent. It's 4 minutes to 11 here, over here. So I'm already. So what will happen is that from the beginning of the next lesson, we'll have a quiz. Okay, I will share you this. I'm going to share you this in the chat, so you can pick it from the chat, or someone will drop it for you on the WhatsApp group for you to have access to it. Let me see if I can drop it on the chat right now, so that you can have access to this document. So meanwhile, any other questions for me before we close?
Yes, sir. I want to ask you something, please.
Okay, go ahead, please.
Okay, sir, you took we learned about three process drawing, which is the P&ID,
Mhm.
BFD, and
And PFD.
PFD.
Yes, yes.
So, sir, I want to ask why knowing the process lines, the thickness of the lines in this three process drawing, are they the same thickness? Is the line the same thickness? If you want to know the lines.
I'm not sure I understand your question very
Okay, what I
well.
mean is that What I mean is that we taught us about three process drawing, and today you said something about kinds of lines, like the main
Mm-hmm.
process lines, the
Mm-hmm.
electrical lines, and the rest of them. And you talk
Mm-hmm.
about their thickness, their thickness. So I want to ask, if you want to determine the process lines in the three process drawing, are the thickness the same thing or different thing?
Oh, okay. They will be the same. They will be the same. The process line will always be thick, while the secondary line is going to be lighter, and this will be the electrical signal line.
Oh,
Yeah, they will be the same. So
okay, sir.
but the thing is that you might not really always see the electrical signal line in the PFD. It depends on how detailed the PFD would be. Excuse me. So, um, so that's basically it. Anyway, that's basically it. Just like this one, this PFD, you don't have the signal lines. It's just the main process line. Okay, right? But this is not a very detailed PFD. But here you have the main process line. So with this, we can begin to understand this properly. And if you look at this one, and let's see if we can find some signal line. Okay, remember I told you about the automatic valve. Sometimes you have N here. I will explain what N means. It means a motor is controlled by a motor valve. It means there's another valve up here, an actuator. The actuator is a motor. So, but we'll talk about this in the next meeting. Okay? So that will be it for now. And thank you very much
Please,
for,
a reminder, please.
okay?
Yeah, about this particular page, sir.
Yes, yes. What about it?
As I asked you to show, please.
Yes, yes, you find it on the chat now. You find it on the chat. If you can download it from the chat, if you don't have access to download from the chat, the organizers will share it with you. I'll share with them and they'll share it.
Okay, sir.
So,
Thank you so much, sir.
all right. So, good night, everybody, and please have a wonderful night rest.
Good night, sir.
See you next week.
Thank you so much, sir. I really appreciate your time with us, sir.
Thank you. Good night.
So yeah, for as many of us that are on the call, even though you've not written your name on the attendance, I'll share it right now. Just kindly fill in your name. Thank you very much. Okay, I don't know whether Rita
Uh-huh.
Masi,
So, Zim,
Rita Masiba, have you filled your name? All right, everyone. Thanks for your time with us. Wishing you a great night's rest. Please have
okay.
a good night.
Good night so much, Blessing. Good night, everybody.
Yeah, well done. Yeah, Lecture Hub. Sorry, I've forgotten your name. Can you please end the meeting for us, like the recording and everything? Can you end it for us, please? You're the only host on the call right now. Mr. Evans. Mr. Evans.